Okay, so let's take a look at some example questions. Now this question that I have up in front of me here, question 0 as it's labeled, asks you to consider the data that I explained last week in tutorial for week 2, and that's available as catvisits.csv on Learn, and it asks what's the unit in this empirical study. So this is an interesting question because I don't actually think it's super obvious what the unit in this study is, at least not compared to some other examples that you might be used to dealing with. So in this case, let's think about what the data actually look like. So the data file that I've uploaded here, well, it has 100 different rows, and in each of these rows, what I'm recording are observations about the cat name, so whether it's Charles or Sadie. I record how long it's been since I last fed them, which is some integer value between 0 and 12, and I record how long they stay on my desk for. And so you can kind of think about these as these three factors forming some sort of infinite population of possible cat visits that I have, right? Because you can think that every visit of a cat to my desk is going to come from either Charles or it's going to come from Sadie. And then it's going to be somewhere between 0 and 12 hours since they were last fed. And then they're going to stay anywhere from, say, 0 to infinite seconds. Now, it's probably not actually infinite seconds at the upper bound, but, anywhere in this range. Right? And so the combination of these three factors represents a single observation. And so the idea is that the unit under study is these visits, right? So it's, cat visits over here, and we'll call that the unit. And so every time that a cat jumps up onto my desk, we can think about this as a realization of a cat visit from this sort of infinite population here, right? And so in this case, it's not either one of my cats, so it's not Charles or Sadie that are the sample. In fact, it's not cat alone. It's the time that they come up, jump on my desk, and stay there. It's that unique visit that we care about. And one way to tell that this was an observational study, which was a question that we asked last time, is to think about the fact that the population of possible cat visits is infinite, right? So there's an infinite number of ways that either Charles or Sadie could come on my desk when they'd been between 0 and 12 hours since they last fed, and they could stay from any possible length of time, right? And so this forms an theoretical infinite population, and we're observing single realizations from this, which means that this is an observational study of cat visits to my desk. Okay, so it's a slightly different empirical study versus what you might be used to seeing, so I figured I'd point that out. But now we'll go to the main focus of today's tutorial, which are maximum likelihood estimators. Okay, so question 1 here is asking us to find the MLE for this parameter p, which we're saying comes from a binomial 1p variable. Now, this parameter is going to represent the parameter associated with a random variable z, and the random variable z will correspond to a 1 if Sadie jumped onto the desk and a 0 if Charles jumped onto the desk. And we're saying that this binomial model is appropriate so long as they're jumping onto my desk independently with a constant probability. So the actual MLE for p in this case is one that was found inside of the course notes, right? So we actually showed that p hat for a binomial model is going to be given by, in this case, z bar, or the sample mean. Right, and so in this course, if you remember this, that's perfectly reasonable. We could just go and compute the sample mean and we would have our answer. What I want to do right now is just quickly run through this math because this is a fairly simple example and I want to get the process ingrained in your head a little bit. So the first thing that we want to do when dealing with these likelihood problems is write out our likelihood. Right, it's a discrete random variable, and our PMF, so if we just want to write over here f of z, with p as the parameter, it's going to be 1 choose p, p to the power of z, 1 minus p to the power of 1 minus z. And this 1 choose p, well, or sorry, that's not 1 choose p. That should be 1 choose z. My mistake there. This 1 choose z is going to either be 1 choose 1 or 1 choose 0, both of which equal 1. And so we can write this PMF a little bit more cleanly as just p to the z, 1 minus p to the 1 minus z. Okay, so we have our PMF, and so we want to write out the likelihood for p, given our sample z. And this sample z, just to reiterate, is going to be a sequence of zeros and ones, where the 0 corresponds to Charles and the 1 corresponds to Sadie. So the likelihood of the parameter p with respect to this sample, it's an independent and identically distributed sample, so we take the product over all of our observations. So we'll say I equals 1 to n, and we multiply the PMF across this whole case here. So that's p to the zi, 1 minus p to the 1 minus zi. Okay? Now, we can do some simplification here, right? So, thinking about some properties of exponentiation, which I'll write them over here, we can think about the fact that b to the power of a multiplied by b to the power of c is equal to b to the power a plus c, right? And so if we have the same base and then we take exponents, we add those exponents. And so here we can look at this first term here, where we have p in the base, zi as the exponent, and we're multiplying it through n times, which means we're just going to add these zi's in the exponent here. So that's going to be p to the power of sum from 1 to n zi. And same thing right over here. We're going to have 1 minus p. That base stays the same across our whole product here. And we're going to take the summation I equals 1 to n, 1 minus zi. And then let's think about these summations we have. Remember that we write z bar is equal to 1 over n summation I equals 1 to n of zi. And what this means is that if we multiply both sides here by n, we get nz bar equals the summation from I equals 1 to n of zi. And so this first exponent we can write as nz bar. So let's fill this in. P nz bar. And then this second one is going to be similar, right? But so we can write the summation from I equals 1 to n of 1 minus zi. We can divide this up into the summation from I equals 1 to n of 1 minus the summation from I equals 1 to n of zi. This first one, we're summing up n ones. That's going to be n. This second one, we looked here and we saw this is nz bar. And so this is n times 1 minus z bar. Okay, and so now we have 1 minus p to the n 1 minus z bar. So this is our likelihood function. And let's take a second to interpret what this is saying. This is saying that if p is the true value for the parameter, this expression right here gives us the probability that we observe our sample z. So the sample z is observed with probability p to the nz bar times 1 minus p to the n times 1 minus z bar. Okay, and so now we can just use some calculus to figure out what the maximum is here. Now we use this trick in statistics all the time, but finding the maximum of this function is the same as finding the maximum of its log, because the fact that this will always be greater than 0 is going to give us the fact that the log forms a monotonic transformation, and so the maximum of this occurs at the same as the maximum of the log of this. And remember, when we say log in stats, the log of x is the natural logarithm. We're always talking about the natural log, and you're only ever going to see it written as log. So just make sure to make this transformation in your head. Okay? But so what does the log likelihood equal? So the log likelihood, which we write as a script L here, log likelihood of pz is going to be equal to the log of our likelihood. Okay? And so now there's a couple properties of the logarithm that if you remember, you will be able to simplify this expression down quite nicely. And in particular, let's keep our aside going over here. The log of x times y is going to be the log of x plus the log of y. Right? And so we can make multiplication into addition, and then similarly, if we take the log of x to the power of y, that's going to be y times log x. Right? And so you can pull the exponents out front. Right? So using the first property here, we're going to get log p to the nz bar. These two are multiplying, so plus log of 1 minus p to the 1 minus, or to the n times 1 minus z bar. And now we can use the second property here to pull the exponents out front. So that's nz bar log p plus n times 1 minus z bar log of 1 minus p. Okay? And now this is our log likelihood, and it's written quite simply. And so the next step is going to be differentiate and set that equal to 0. Okay? And so what I'm going to do is I'm going to use the notation L prime of p, and I'm using this notation to mean the partial derivative with respect to p of L, p, and z. And so we're using this notation to emphasize that for our case, this z is being treated as though it's constant, and we're just differentiating with respect to our parameter p. Right? So what does this derivative actually equal? Well, for this first term, this nz bar, that's just a constant, so we'll leave that sitting out front here. And the derivative of log p is 1 over p. So that's times by 1 over p. And then plus, again, this n times 1 minus z bar is constant. And so now we want the derivative of log 1 minus p. So that's going to be 1 over 1 minus p times the derivative of 1 minus p, using our chain rule there. And so that's going to be a -1. So writing this down a little bit more neatly here, we have nz bar over p minus n times 1 minus z bar over 1 minus p. Okay, and now we know that because we're trying to maximize this function, we want to set this equal to 0 to find the critical points. Okay, and so to do this, we're going to bring this term over to the other side and start trying to isolate for p. Okay, so doing that gives us nz bar over p equal n times 1 minus z bar over 1 minus p. Now what I'm going to do is multiply by the 1 minus p, bringing it to the other side, and I'll divide by this n z bar at the same time so that we can write 1 minus p over p equals n times 1 minus z bar over nz bar. These n's are going to divide out here, and we can write this right-hand side, or this left-hand side, as 1 over p minus p over p, so that's -1, right? And so now we can pull the 1 over to the other side, and that leaves us with 1 over p equals 1 minus z bar over z bar plus 1. right? This plus 1 we can write as z bar over z bar. So that's going to be 1 minus z bar plus z bar over z bar. Those cancel out. And so we're left with 1 over p equals 1 over z bar, or alternatively, p equals z bar. Now, I could have been a little bit carefuler with my notation here, and so I'll go back through and show you what I mean. As soon as we set this equal to 0, really what we're doing is we're finding the value of p such that this expression is true, and we tend to call that value of p p hat. Okay? So I should have been a little bit more careful and used p hat throughout this math here, so I'll just come and fill that in now. Right? And the idea is the estimate that we're finding here, our maximum likelihood estimator, is going to be p hat, and that's the value that solves this equation equal to 0. So just to be clear on the notation here, that can be a little bit confusing, but I'm not saying that the parameter p equals z bar. I'm saying that our best guess as the estimate of this parameter equals z bar. And so that's the process of finding the maximum likelihood in the binomial case. Now this again was all shown in the notes, but I hope that walking through it sort of in explicit detail here at least reinforce some of these ideas. But ultimately what we're seeing is that the maximum likelihood estimate is the mean of z bar. So what we can do then to answer our question, which to remind us is we want to know what the estimate is where this p is representing the probability that it's Sadie jumping up. In order to actually compute that for our data set, I can open up RStudio here, and the variable that we care about, if I have my cat visits over here, I define this cat name bin variable. That should be available on the cat visits data frame for you. And that cat name bin is exactly what we defined z to be. So it's a 1 if it was Sadie, it's a 0 if it was Charles. And so all I have to do then is call the mean of cat name bin. And if I run it, you see the mean was 0.12. Right, so coming back into our question here, what we find is that the maximum likelihood estimate for p is 0.12, or 12%. Okay, and so that would have been the answer given to question 1. So that was a little bit more detail than what was probably necessary, but hopefully that detail was helpful. And we can jump on to the next question now. Okay, so taking a look at question 2, we have a question that's actually kind of similar to question 1. So ultimately in this question, we want to find the MLE for this parameter pi, and pi here represents the probability that this random variable y is equal to some value. So pi 0 is the probability that y equals 0, and pi 1 is the probability that y equals 1, and so on. Now, this random variable y is what maps onto our hours since fed variable. Now the hours since fed variable, if you remember from the previous video, is an integer value somewhere between 0 and it can go up to 12. And we're assuming that it's independent of which cat's jumping on the desk, and that then it can be described using these 12 probabilities. And so say that pi here is, the vector from pi 0 down to pi 11. Now the reason that in theory we can describe these using these 12 probabilities, even though we can have up to 12, is because of this identity here. So probability that y equals 12 we can write in terms of the other 11 probabilities. Now to make things a little bit easier for us notationally, I'm actually going to introduce a 12th probability here, or a 13th rather. So we define the pi vector here to be inclusive of pi 12. where pi 12 is just the expression that we have right here. Looking at this problem, you might notice that this is actually a multinomial question here, which multinomial that was covered in the course notes as well. So once again, I'm going to walk through how we could derive this probability, and I'm going to do it specific to this iteration here to once again try and give you some more experience working with these likelihood functions. But if you happen to know this is multinomial and off the top of your head you know what that means the MLE will be, feel free to fill that in and move on. So the first thing that we're going to do working with our likelihood function is to write down our likelihood function. Okay, so we're going to start with L, and L is going to take the two parameters. The first is going to be pi, and we're writing it with the underline to indicate that it's a vector. And the second parameter is our vector y. So y is going to be observations of this hour since fed variable. And as with any likelihood from a sample of independent realizations, we take the product over all of our observations. So that's the product from I equals 1 up to n, where n is the number of observations we have. And then it's the probability that the random variable we care about, so in this case the probability that y is equal to yi, assuming that we have the parameter vector that we have specified as an argument. So here we know that the probability that y equals yi, well, if yi is 0, this is going to be pi 0, and if yi is 1, this is going to be pi 1. And so in general, we're going to be able to write this as pi sub yi. Okay, so this is going to be the product from I equals 1 to n of pi sub yi. Now, if it was me looking at this for the first time, I would be thinking, how do we go about dealing with this, right? Because this is an expression that looks quite simple, right? It's just a product of a number of probabilities. But how do we deal with this? How do we deal with the fact that the yi's are in this subscript here? So there's actually going to be two ways of addressing this, or at least two obvious ways of addressing it to me. And the first way that we could do is to write out what this pi I actually is, or pi yi rather. So we could write pi yi as the multinomial probability, which is going to be given by something like pi 0 times, or to the exponent of the indicator function, that yi equals 0, times by pi 1 times the indicator function, that yi equals 1, times by up to pi 12, the indicator function, yi equals 12. Why don't we cross that out and say indicator yi equals 12, fit it in. Sorry about that. Now, this expression here, to define the notation clearly, the indicator function that yi equals j is a function that takes on a value of 1 if yi is j, and it takes on a value of 0 otherwise. And so then basically what we're doing here is if yi is, say, 0, then this first exponent will be a 1, and all of the other exponents will be a 0. And so then we take pi 0 to the first power, and then everything else is to the 0th power, so they all become 1s. Similarly, if, say, yi was 2, then we would have pi 0 to the power of 0. Well, that's 1 times pi 1 to the power of 0. That's also 1, and then we'd select out the pi 2, and then the rest of the terms would have a 0 power and would go to 1 themselves. So one way that we can deal with this is to actually explicitly write out this expression, plug it in, and simplify in the way that we normally would. Now you can feel free to do this, and if you get stuck trying to do this, you can reach out to me. I'm more than happy to answer your questions on them. Instead, what I'm going to do is try and reason through it, thinking intuitively about what this product sequence looks like. So it's less following a mathematical recipe, but it might make a little bit more sense for you. So if we think about what this product is, well, this is the product of y1 times by the product, or times by y2, pi y2, times by pi y3, and so on, up to pi yn. Now each of these pi's, pi y1, pi y2, and so on, each of them are going to be in the set of pi, right? So they're going to all be elements from either pi 0 or pi 1 up to pi 12, right? And each of them will be this depending on what the observation of yi is. And so if we open up the data for a second here, just to take a little aside, so we can pull open RStudio, and you can see here I have this data file actually opened up, and we're looking at this hour since fed variable. And you can see that the first few observations are 10, 8, 7, 11, 6, 7, 6. Okay, so the first 7, say. So the pi's that correspond to these will be pi 10, pi 8, pi 7, pi 11, pi 6, pi 7, pi 6. Okay, so if we come back over here, we have, all right, so I just went and filled those in because it was easier to do that way than to try and do it off of my memory. But so here we have the first 7 observations. So what I'd like to point out here is that this product sequence that we have here can be written as exponential powers of the values pi 0 through pi 12. And so if we're just looking at these first 7, we're going to have a 0 exponent on the first, or on the 0th, and on the first, and on the second. Now pi 6 has 2 observations in the sample. Pi 7 has 2 observations in the sample. Pi 8 has 1. Pi 9 wasn't anywhere, so that's a 0. 10 has 1, and 11 has 1. And pi 12 has 0. Right? And so throughout the first 7, you can see that just by putting on some exponents on these values, we can represent the first 7 products. But more generally, if we were to define, say, n0 to be the number of 0 observations, and we define n1 to be the number of 1, and so on, up to n12, which we're defining to be the number of 12s that we observe, then by taking this definition, the product from I equals 1 to n of yi, or of, sorry, pi yi, right? So this is the likelihood. Well, this could be written as the product from j equals 0 to 12 of pi j to the power of nj, right? So all we've done is we've taken out each of the pi terms that we care about, and we raised them to the exponent, which constitutes the number of times that it showed up. So when we multiply through by all n observations, we're just really counting how many times did pi 0 and putting the right exponent on there, and how many times did we see pi 1, putting the right exponent on there, and so on, up through pi 12. And so we can write this as this, or this is another way of writing our likelihood. And it's a way of writing our likelihood in terms of our parameters directly, so this is a little bit easier to work with. Okay, and from here, the next step, as is usually the case, is to write down our log likelihood. So we want the log likelihood, just give it the 2 parameters still, and that's going to be the log of our likelihood, which here we just plug in this product from j equals 0 to 12, pi j to the nj, and then using our log rules again, the product becomes a summation, and each of these exponents can come out front, so we can write that's the sum from j equals 0 to 12 nj log pi j. And so this can be our log likelihood here. And so then the next step to find the MLE is to consider the derivative of our log likelihood with respect to our parameters. Now here, we want to pay particular attention to the fact that this is multivariate. And so we can't just take the derivative of the log likelihood with respect to the vector parameter here, or rather we can do this, but really what we're saying here is that this is a derivative with respect to each of the parameters in this vector. Now the thing to note is that this expression looks basically the same for any of the values of pi, right? If we plug in pi 0, then all that's changing is this j and this j. And otherwise, looks effectively exactly the same. So what we want to do then is just consider the partial derivative of our log likelihood, which I'll write to the log likelihood like this, with respect to, say, the kth pi. Right, and so we'll take it with respect to pi k, and so that's holding all other entities constant. And so for j not equal to k, we'll notice that this whole expression here is constant with respect to pi k, right? And so it's 0 everywhere that j is not equal to k. And then when j is equal to k, we get the nk coming out front, and then the derivative of log pi k with respect to pi k is 1 over pi k. All right, so these will be the derivatives of every one of the observations we have. Now you might be wondering, well, the next step that I'd want is to set this thing equal to 0. Right, we want to set this equal to 0 and then solve for pi k, but notice that that would mean that pi k nk equals 0, question mark? Right, and so what's going on here? Why doesn't this work? Well, remember up at the start, we were talking about redefining this vector to be pi 12 here, right? And so we actually know that there's only 11 uniquely defined pi's, and that pi 12 has to follow this relationship here. And so we essentially have too many parameters in our model now. And so we need some way to rectify this situation. And so depending on whether or not you've seen constrained optimization, what I'm about to do may or may not make a ton of sense, but just bear with me throughout this, and I promise it will become clear in a moment. But whenever you want to do a constrained optimization problem, so we're trying to maximize the likelihood here, the log likelihood, and we have this constraint. We need to constrain the sum of j equals 0 to 12 pi j equals 1. Okay, so this essentially acts as our additional equation that we want to work with here. But when you're doing a constrained optimization problem, the way that you end up including this is to add an additional parameter that functions in this constraint. And so the way that we're going to do that is, instead of working with the likelihood directly, so say the likelihood is, or the log likelihood rather, is this summation j equals 0 to 12 nj log pi j, what we do is we take the likelihood and we add on lambda, which is just some parameter that's going to be a placeholder, times by the constraint that we have here when it's made equal to 0. So this constraint here is the same thing as saying 1 minus the sum of j equals 0 to 12 pi j equals 0. And so we're going to add on lambda times by this term, right? And so really we're not changing the log likelihood here, because 1 minus the sum from j equals 0 to 12 of pi j. Well, this term that we've added on here is still 0, right? Because 1 minus the summation here has to be 0. And so we've just added 0, but we've added 0 in kind of a clever way. That means that now we're going to actually be able to correctly solve this equation. And so when we add that on, we'll add it on over here as well. So plus lambda 1 minus the sum from j equals 0 to 12 pi j. And what that means is that when we take our derivative, right, so we looked at our derivative up here and we got this nk times 1 over pi k. So when we take the derivative of this constrained likelihood with respect to pi k, we're still going to get that as the first term, so that's nk times 1 over pi k. But now we're also going to get minus lambda, right? Because we're going to have lambda times by, in this case, it's going to be a 0 anywhere that's not j equal to k, and otherwise it's going to be a -1. So we subtract off lambda. And now you can see that we can actually set this thing equal to 0, right? If we set this equal to 0, then what that means is that we're going to have nk over pi hat k is equal to lambda. And now, doing our quick little rearrange, that means that pi hat k is equal to nk divided by lambda. Okay? And so you're probably wondering, well, what's this lambda, right? This is great. We've gotten an expression for pi hat k, but what does lambda equal? And there's a couple of ways of getting there. The easiest way, in my opinion, is to consider the fact that we know that in order for this to be a valid probability, we have to have the fact that pi, or the summation from k equals 0 up to 12 of pi hat k, this has to equal 1. And this was the constraint that we put in, right? This is the same constraint right here, but it's a sum to 1 probability constraint, so we know that has to be the case. And so if we just plug in our estimates here, then we would get the summation from k equals 0 to 12 of nk over lambda equals 1. Sorry, that should not be a 12, that should be a lambda. And so we can write this as 1 over lambda times the summation of k equals 0 to 12 of nk equals 1, which is the same thing as saying that lambda is equal to the sum from k equals 0 to 12 of nk. So now let's consider the summation here for a second. Remember that nk is defined to be the number of observations with k. So n0 is the number of 0 and n1 is the number of 1. And so in this summation, we're adding up the number of 0 plus the number of 1 plus the number of 2 and so forth up to the number of 12. And so we're just adding up all of our observations here. So in other words, the summation of all of these things has to give us n, which was our total number of observations. Okay, so in other words, lambda being n means that our estimator up here we can write as nk divided by n. And this is going to be true for k equals 1 through 12, or k equals 0 through 12. So again, this is the intuitive estimator. We're looking at the proportion here, and this is the estimator you would have found in the course notes. But hopefully seeing it like this is just a different way to work through things. And so now the question becomes, well, that's great, but can we see those estimators in RStudio? So now we're over here in RStudio, and what I want to do is I want to try and form those maximum likelihood estimates for each of our values between 0 for pi 0 to pi 12. So the first thing that we need to do is get our n's out of there, right? And so if we think about the table command, and we pass into the table command the variable that we're interested in, so that's the our since fed on our cat visits object, well, table is going to give us this table that tells us for 0 we had 3, for 1 we had 2 observations, for 2 we had 4, and so these values given out of table are actually going to be the n values that we care about. So I can do this. I can assign my n's to it. And then if we take a look, we can see that, say, n's 1 is going to be that value of 3. Okay, now we don't actually want the number, right? Because our maximum likelihood estimate was the number scaled by the total number that we had. And so the total number that we had is 100, which we can also see just by going sum on the ends, right? So we have 100 total. And so what I can do here is I'll define pi to be equal to ends divided by the sum of ends. Okay, and now if we take a look at what pi is down here, we can see that pi is a set of probabilities, 3%, 2%, 4%, 10%, and so on, up to pi 12. And so right here, we have our maximum likelihood estimates for all of the pi factors for the multinomial model for the hours since fed variable. Okay, so taking a look at question 3 here, what we notice is that we want to find the MLE for a bunch of different quantities. And so let's take a look at the quantities that we're thinking about and try and piece together how we're going to do it. So the first one is we want the probability that 3 sequential visits are from, in order, Sadie, then Charles, and then Charles again. Okay, so this is saying, what is the probability that 3 visits in a row go Sadie, Charles, Charles, or using the notation from question 1, that's the probability that we observe a 1 and then a 0 and then a 0. Okay, and we want the maximum likelihood of this. Now, the second part wants to know what is the median hours since fed, the maximum likelihood for the median hours since fed. And so what we want to know there is the, if we think about the value probability y less than or equal to some value m equals 0.5. And that's going to be the median here, m. So we want to fill in what is this value of m in the maximum likelihood situation. Now we want also the variance of z and the variance of y. We want the MLEs of these two factors. And then assuming independence, we want to know what's the probability that a visit is either from Charles 4 hours since they have been fed, or Sadie 8 hours since they have been fed. So this is the probability that we have a visit which is Charles and 4 hours since fed, or Sadie and 8 hours since fed. Okay? And so the thing that each of these have in common, all 4 of these, is that, well, one, they probably seem a little bit complicated if you have not put together how we go about approaching these in this class, right? They are more complicated than just asking for the maximum likelihood for a distributional parameter. But the second thing is that each one of them are functions of the distributional parameters, right? So if we think about, say, number 1 here, this is the probability of some sequence of events. Well, these sequences of events, the probabilities that they occur, are defined based on the fact that we have a binomial 1p model, right? And so if we knew p, then we could just compute this probability. Similarly, the median hours since fed, well, we know that if we knew all of the pi that define y, right? So if we knew this whole vector, then we could compute this. We could figure out what the value of m such that this is true is, and so on with the variances and this final probability model down here. And so in general, whenever we're in a situation where there is some function of a parameter that we can estimate, so let's say g of theta, if we are interested in the MLE of g of theta, then by the invariance property of MLEs, so this is the invariance property, we know that the MLE of g of theta is g of theta hat, where theta hat is the MLE. Okay? And so this is always going to be true for functions of our parameters here. And so what we can do now is we can look at how we go about solving these invariance property type questions. And it's going to be following a similar set of steps, but so let's take a look. And I think I've ordered these roughly so that they can become increasingly difficult, but let's take some time to figure out how we'd go about it. So for question 1, we're looking for the probability that we observe a 1 and then a 0 and then a 0. And so the question becomes, we know that p hat is equal to 0.12. Found that in question 1. And we know that these data are being drawn from a binomial 1p distribution. And so then thinking about this invariance property that we have over here, what we want is we want to express the probability that we get a 1 and then a 0 and then a 0 as some function of p. Okay, so what function of g can we do for that? So the way that I would recommend going about this is just to write out what is this probability, right? So first thing is we can write this out sort of more explicitly. So I believe that I called the random variable z. So we're looking for the probability that z equals 1. And then on the next draw, the probability that z equals 0. And then on the next draw, the probability that z equals 0. Now we have 3 consecutive draws from an independent random variable, and so we know that these just multiply. So we have the probability that z equals 1 times by the probability that z equals 0 times by the probability that z equals 0. Okay? Now, probability that z equals 1, well, that's p. By definition, we have that being p. Probability that z equals 0 is 1 minus p. And probability that z equals 0 again is 1 minus p once more. And so now we have this function, g of p, that gives us the quantity we want. And so by the invariance property, the MLE of g of p is g of p hat, which in this case is going to give us p hat times by 1 minus p hat squared, which in this case is going to be 0.12 times by 1 minus 0.12 squared. Okay? So that's the first one, and that gives us the MLE of the probability of that sequence of events. So let's take a look at part 2 now. Now, part 2 says the median hour since fed. Unfortunately, this came from an earlier version when I was treating this hour since fed variable slightly different. And so we're actually not going to look at part 2 because it's actually not as straightforward given the distribution of the hours since fed. And so instead of doing that, why don't we consider the probability that y is, say, in the interval from 1 to 6. Okay? So what we want to see here is what's the maximum likelihood estimate that the hours since fed is somewhere between 1 and 6. And sorry, this should have some dots in there in that set. Okay? And so again, the question becomes, what is a function g of, in our case, pi, such that it equals the probability that 1 is less than or equal to y, which is less than or equal to 6. Now in this case, it's actually a more straightforward situation here, or perhaps maybe not more straightforward, but this is going to be equal to the probability that y equals 1 plus the probability that y equals 2, and so on, up to the probability that y equals 6, right? Because we know that y is a discrete variable. It takes on integer values between 0 and 12, and each of these are mutually exclusive events, and so we can just sum up these probabilities here, right? Now, according to our parameters, this is going to be pi 1 plus pi 2 plus pi 6, right? Now, I actually don't have these memorized off the top of my head, but what I do know is that this being the function g, if we want to know what the maximum likelihood is, then that implies that the maximum likelihood is g of pi hat, which in our case is going to be pi hat 1 plus pi hat 2 plus fill in the blanks up until pi hat 6. And because I still have RStudio up and running here, we can come over here and we can see that really what we're wanting to do is sum these values, right? But I've stored these values as pi in this ratio, or in this variable. And so what I want to do is take pi, and pi 1 is going to be at 2, right? And pi 6 is going to be at 7 because we're off by 1 here. And so if I take pi 2 to 7, that's going to give me each of those probabilities. And so all I need to do to find the MLE of this is to go sum from pi 2 to 7, and that gives me 0.36. And so what this means is that the maximum likelihood estimate for the probability that y is between 1 and 6 is going to be equal to 0.36. Okay, so sorry about having to change that question last minute there, but did not want to end up overly confusing anything. So what about number 3? Number 3 is looking for the variance of z and the variance of y. Okay, so let's go down and try and write these out. And again, the process is going to be the same. We want let's start with z, right? So z, just to remind ourselves, is a binomial 1p. And so what's the variance of z? Variance of z equals what? Well, the variance of a binomial random variable is going to be equal to n times p times 1 minus p, which means that our MLE for the variance of z, also to, I guess, finish the thought here, n is just 1, and so this is p times 1 minus p, which we can think of as the function g of p. And so the MLE is going to be g of p hat, which in this case is going to be p hat times 1 minus p hat, or in other words, 0.12 times 1 minus 0.12. Okay, and what about y? Well, y we know is our multinomial indexed by this pi parameter here. Okay, and so the variance of y, well, that might be slightly harder to pull from memory. And the way that we're actually thinking about our realizations of yi are not directly the way we would normally think about the multinomial, right? So this is perhaps somewhat of a confusing statement here, because normally with the multinomial, you're going to think that y is then some vector realization, right? And so where in fact we actually are only ever making one observation and we're recording it. So these two things, while they're equivalent to think about in some mathematical sense, which is why we can derive their MLEs using a similar process, the way we actually treat y is slightly different. And so we'll have to think about the variance of y by going back to the definition of variance, right? And so remember that the variance of some random variable is going to be equal to the expected value of that random variable squared minus the expected value of the random variable squared. Okay? And so we can think about doing each of these. The expected value of the random variable squared, well, what values can y take on? Y takes on any of the values from 0 to 12. And so the expected value of it squared is going to be the sum from 0 to 12. We take y squared times by probability y equals y, which is, as we were seeing in the previous question, it's the sum from y equals 0 to 12 y squared times by pi of y, right? So 0 squared times pi 0 plus 1 squared times pi 1, and so on. Okay, and now the expected value of y, which we'll need to plug in here, this is just going to be the sum from y equals 0 to 12 y, instead of y squared, times by pi y, right? And so what this means for us in terms of our variance is that we can write the variance of y as some function g of pi, which is going to be equal to the sum from y equals 0 to 12 y squared pi y minus the sum from y equals 0 to 12 y times pi y, this whole quantity squared. Okay? So we can open up our RStudio again. And now that we're in RStudio, we can think about computing those two values. So the first one that we want to compute is the expected value of y squared. So I'm going to call this EY squared. Apologies that that's not the best name in the world, but bear with me. And so there's going to be a couple of ways that we could think about doing this. And again, you're not expected to write this R code, so I'm walking through what I'm doing, but just know that any R code you need in this course, you'll be given. So the one way that we could do this, the first way that comes to mind, is we're going to end up wanting to sum over some values. So that we'll start with our summation here. And then we want those y squared values. And so we know that y runs from 0 to 12 in a sequence by 1. And we want those values squared. So this is right here, this sequence 0, 12 by 1 squared. That's going to give us the squares along the values 0 to 12. And each of those need to be multiplied by pi. And so if we do this, then this is going to give us that the inside of our summons. And so summing up over those will give us the expected value of y squared, at least using our pi hats instead of our pi's. And now we want the expected value of y, which this one's a little bit easier to do. So we can go sequence 0 to 12 by equals 1. We don't need to square it this time, and we can multiply it by pi. And so that gives us our expected value of y. And now our MLE of variance of y is going to be the expected value of y squared minus the expected value of y, and we square this quantity. And so we can take a look at what the MLE of the variance of y is, and we compute that to be 11.4739. So coming back here and finishing up what we're saying here, that means that our MLE of the variance of y is going to be g of pi hat, which was 11.4739. And so those give us the MLEs for the variance. So now let's take a look at the last part. So part 4, we've assumed independence, and now we want the probability that a visit is either from Charles 4 hours after they've been fed, or Sadie 8 hours since they've been fed. Okay, so we want the probability that a visit is going to be Charles and 4. It's a very bad squiggly. So Charles is a 0 in terms of our y variable, and 4 hours since they've been fed. Or Sadie is a 1, and I believe it was an 8. Okay? And so to put this into notation using our random variables, we want the probability that z, the probability that z equals 0 and y equals 4, plus the probability that z equals 1 and y equals 8. And so what we would actually need here is the joint probability of z and y. But luckily in this question, I stated that these things are independent, and so we can write this as the probability that z equals 0 times the probability that y equals 4 plus the probability that z equals 1 times by probability that y equals 8. So this guy, z equals 0, well, that's 1 minus p. Y equals 4, that's pi 4. Plus z equals 1, that's p. Y equals 8, that is pi 8. And so this is now going to be a function here of these two parameters, p and pi. And because of that, we can now fill in the MLE as g of p hat and pi hat, which is going to be 1 minus p hat pi hat 4 plus p hat times pi hat 8. Now I'll let you fill in the actual values here, but I'll just point out one very important thing. We never found the MLE for the joint distribution of y and z, right? We found the marginal distributions of y and z by themselves. Now in this case, because y and z are independent, and because when you set up their joint distribution, we have functional independence between p and pi, which essentially means that when we start taking the derivatives, any of the derivatives with respect to p are not going to matter with respect to pi, and vice versa. They're not going to have each other in it at all. We can essentially solve these two things independently of one another and plug them in. If there was any reliance of y on z, or any reliance of p on pi, or vice versa, then we can't just assume that this is going to work out. Worked out in this case because we assumed some independence, but otherwise we'd want to consider their joint distribution and find the MLEs in the joint distribution. Okay, so just something to be mindful of there. It's not going to matter in this situation, but it might matter in the future. So just watch out for that and make sure that you've actually made certain that the joint distribution that you're working from is the one that you actually want. And so there's some examples on how we're going to use the invariance property, which, to clarify once more, means we're looking for the MLE of some function of our parameter, and all we want to do is apply that as the function with the MLE plugged into it. So the strategy is always going to be try to find the function of the parameter that it is that you're interested in, and then plug in our MLE estimate into that function. Okay, so taking a look at question 4 here. Question 4 comes with a little bit of a story that I wrote. So we often say that Isaac Newton gets credit for inventing calculus, though some people are definitely going to be angry that I said that. That means that Isaac Newton is to blame for much of the frustration that you're going to face throughout your undergraduate studies, and he also will deserve 0 credit for answering the following question. If we assume that x1 through xn are an independent sample from a uniform 0 theta distribution, find the MLE of theta. So of course, the history setup here is entirely irrelevant for the math that we're solving, but I just wanted to pay special attention to some situations where the common way that we solve maximum likelihood problems will not work. So in particular, we know that a uniform 0 theta distribution is such that we have constant probability density from the interval 0 through theta. So if theta is some value right here, then we know that we have basically this rectangle of density here, right? And it's constant across it all. And in particular, what that has to mean, based on the fact that integrating the PDF gives us 1, means that the value that the PDF takes on is constantly 1 over theta. So in other words, if we have a random variable y, then f of y is going to be the density function, and it's 1 over theta. But importantly, it's 1 over theta for y in the range 0 to theta. Okay, and so I'm asking a fairly simple question here, and that's what's the MLE for theta? So we might think to try and use the standard likelihood process that we've been using. right? And so let's write that down. So we take our likelihood function. It's a function of theta, and in this case, our sample is going to be x, right? And we know that that's the product from I equals 1 to n of our density in this case. So the last few examples have used discrete random variables, but we just insert our density in wherever it's relevant. So that's going to be f of xi, which in this case is going to be I equals 1 to n of 1 over theta. Every one of them has constant density, right? And if we multiply 1 over theta n times, right, just thinking about what that is, it's 1 over theta times 1 over theta, and so on, that's going to give us 1 over theta to the power of n. Okay? And so we find this very nice, simple likelihood function, 1 over theta to the power of n. And so what are we going to do here? Right? Well, the normal technique is going to be differentiate this with respect to theta, or typically actually take the log of this, right? So we'll write down our log likelihood. So that's going to be the log of 1 over theta to the power of n. Remember that if we divide things, that's going to be a subtraction in the logs. So that's the log of 1 minus the log of theta to the n. Now the log of 1 is always going to be 0, so we're just going to be left with minus log theta to the n, and we can bring down that n out front. So that's minus n log theta. Okay, and so now if we take the derivative of this, so using the notation L prime of theta, that's going to be negative n over theta, and we'd want to set this to be equal to 0. So we'd want L prime of theta hat equaling 0, which would mean what exactly? So we'd have negative n over theta hat equals 0. And how can we go about doing this? Of course, there's nothing here that's going to make this work, right? We don't have a value of theta that's going to make this work. I mean, of course, if we take theta off to infinity or negative infinity, we're going to get the correct value, but we can't take theta to be infinity or negative infinity. And so what does this mean? Does this mean that there is no maximum likelihood? And of course, I wouldn't be asking you this question if there wasn't a lesson to be learned here. And that's the lesson that we want to teach, is that sometimes calculus is not going to be our friend, right? Sometimes what we want to do is fall back on our understanding of what we're actually trying to do. And our understanding of what we're trying to do is maximize this function, okay? It doesn't matter how we maximize this function, so long as we find the value of theta that makes this the most likely. And there's an important consideration here, okay? So let's consider just a set of observations. And let's say that my observations are 0.1, 0.22, and 0.08, for instance. Okay? So just hold these sets of observations in mind while I start talking through some things that we can think about here. So the function 1 over theta to the power of n, what happens as we increase theta? Okay, as theta gets big, then 1 over theta is going to decrease, right? So if you think about plugging in, say, theta equals 1, implies that this is going to be equal to 1. And if we plug in theta equals 10, then this is 1 over 10 to the power of n. And if we plug in theta equals, 100, it's going to be the same thing. And so these, as theta gets big, then L of theta gets small informally, right? In other words, we would say that the likelihood function is inversely proportional to theta. It's proportional to 1 over theta. So what this means intuitively for us is that we want to take a small value of theta, right? We want to take a value of theta that is close to 0, and as close to 0 as we can get. Now if you think, if we actually plugged theta equals 0 in here, then our likelihood is going to be equal to infinity, right? 1 over 0. Now of course the uniform 0, 0 is not really a distribution we're particularly interested in. That's going to be a distribution that only ever spits out zeros, so we're not super interested in there. But we want to take theta to be a small value. Okay? So let's think about those numbers that I said we could observe up here. So it's 0.1, 0.22, and 0.08. Now, the likelihood as we wrote it is going to be 1 over theta cubed, if this is our sample. Okay? And we know that theta is supposed to be a small value. And so what if I took theta to be equal to, say, 0.1? Okay? Well, 1 over 0.1 is going to be, or rather 1 over 0.1 cubed is going to be the same thing as 1 over, let's write that as 1 over 10 cubed, right? So that's going to be equal to 10 cubed. Right, that's a pretty big number. It's 1,000. And so is this going to be acceptable? And this is somewhat of a trick question here because, in fact, we know that theta cannot be 0.1. And why do we know this? Well, I made an important note up here that y is in the interval 0 to theta. Every y that we observe has to be less than or equal to theta. And take a look at right here, 0.22. 0.22 is larger than 0.1. And so the probability that y is, the probability that y is 0.22 is going to be 0 because because it's a continuous variate. But if we take f of 0.22 given theta equals 0.1, this is going to be equal to 0. And that's a problem, because what this actually means is that if theta was 0.1, the likelihood that we observe this sample is 0. There is no possibility that we observe this sample if theta is equal to 0.1. Okay, so now we have this conflicting realization. We want theta to be small. However, we need to still be able to observe all of the values in our sample. So what's the smallest possible value we could have observed for theta? The smallest possible value we could have observed for theta is this 0.22, right? Any value that's less than 0.22, so if we have values that are smaller than 0.22, then 0.22 becomes impossible to have been observed because 0.22 would be bigger than theta. Conversely, if we take anything that's bigger than 0.22, well then we could make the likelihood larger by dropping the value down to 0.22, right? Because small theta is good theta. So in other words, when we write down the likelihood and we see that the likelihood of theta given our sample is equal to 1 over theta to the n, well, this is only true assuming that theta is at least as big as the largest x that we have. Okay? But so what we also can see right from reading off this is that we want theta to be as small as it possibly can, but the smallest that it can be is xn, which is the same thing as the maximum over all of our x's. Okay? And so what this means is that our MLE is going to be the maximum observed value. So it's important to note that sometimes we come into these tricky situations where we can't just use the standard process of writing down the likelihood finding the log likelihood, taking a derivative, setting it equal to 0. So it's important every time that you see your likelihood function to think about what's happening. And if you ever compute the derivative and it's something like this, you need to solve this impossible relation here, you should go back and consider, it's possible that a mistake was made somewhere in the math, but it's also possible that there's a way that you can solve this problem without resorting to calculus, where you can think about what you're actually trying to do, which is make the likelihood as big as you can. And remember that if the parameter is showing up in the interval here, then we need to make sure that our sample actually has any likelihood of observing it. Once you've seen this kind of trick, it's not as difficult, but it certainly can be a weird one to wrap your head around. So I'd encourage you to go and try it yourself and to see how it would shift, for instance, if we were looking at something like the uniform of, say, theta to 100. Okay, so consider something like this. It's going to be a similar process, but really try and reason your way through it and convince yourself of what the MLE has to be. So I wanted to leave you with a challenge question this week. So I'm not going to give you the answer right now, but if anyone's interested, please just send me an email and I'm more than happy to make up the answer for you. But what I wanted to do is really stretch our understanding of likelihood with this question. And so we're considering for a moment that cat visits data again. Okay, and what we're going to do is we're going to call the time that the cat visited to be this random quantity x. And what we're going to do is we're going to make the assumption that x given y and z is a Poisson random variable, where the parameter is y plus alpha, or is lambda plus alpha y plus beta z. If we make that assumption and we still assume that y and z are independent of each other, what we want to do is write down the likelihood function of all of the parameters involved in the joint distribution of x, y, z. Now, if you want to keep going, you can try and determine the system of equations that we would have to solve. And if you really, really are interested, you can use the numerical methods to determine it, and given the data that are available on the course website. So just to clarify what we're saying here is we're saying that x is represented or representing the time of the visit, or the visit length variable. And we're saying that xi given yi and zi follows a Poisson distribution. It's lambda plus alpha yi plus beta zi. And so if you consider the joint distribution xi, yi, and zi, it's going to depend on the parameters here. So it's going to depend on the parameters lambda, alpha, beta, and it's also going to depend on the parameters from yi and zi. So we saw those as p and pi, right? So it's going to depend on a whole bunch of parameters that we have here. And what I'm saying is consider writing down, so if we define this to be theta, then what's the likelihood of theta with our sample x, y, and z? Now, I'd like to warn you in advance, this is certainly not an easy question, but if you try and piece through by, following the steps of what is the distribution function? So we want to find the distribution of, in this case, it's going to be x, y, z for a single observation. And then two, you fill in these details into the likelihood. And then we know what we're doing once we have the likelihood is, in general, we want to find the log likelihood. And then we want to differentiate, right? So these are the general processes, and they're going to work mostly. Now what you get out of here, you're not probably going to be able to solve by hand, but if you are willing to do a little bit of programming effort, you can find the answer in R. Now again, this is a challenge question. It's not something that I necessarily expect to spend the time doing, but if you're interested, it's worth a go, and I'm more than happy to show anyone who is interested how it's done. So let me know if you do give it a go. I'd be really interested to hear how that went for you.